All right, so this is the last portion of section 12.6 on cylinders and quadric surfaces. A little bit shorter than the last section. Now that we have all the different quadric surfaces covered, all we're really going to add on in this section is what happens if we add shifts to those quadric surfaces. What if I want to, vertically shift them up into the air, or horizontally shift them left and right in the X direction, or left and right in the Y direction? So yeah, we're just going to do a little bit more analysis of these quadric surfaces. Little recap from last time. One thing I now included, last time we kind of learned by example. Here I have a chart that kind of summarizes all the big findings, kind of the Cliff Notes version of what we did in the first day of this section. You'll notice in the chart, it's assuming that the axis of symmetry is always with respect to the z-axis. That won't always be the case in the problems that you do, but you just change the equation accordingly if you want the axis of symmetry to be the y-axis or the x-axis. So everything's assuming that the z-axis is the axis of symmetry for the chart. And so really we had, just to summarize a little bit without repeating everything from last time, we had two main breakdowns of these quadric surfaces. We had cases where x squared, y squared, and z squared all showed up in the equation. So all of the variables were quadratic. And that was for, we had, we had the ellipsoid, we had the hyperboloid of one sheet, and the hyperboloid of two sheets, and we also had the double-sided cone. Okay. I feel like I'm missing one. Oh, that's it. That's 4. There we go. And then the other situation we had is where only 2 variables were squared or quadratic. So you have one linear variable, and that was the elliptic paraboloid and the hyperbolic paraboloid. And we spent a lot of time last time looking at these distinctions of, okay, once you can, so that's the first thing I would do is break it down into one of these two categories. The first thing you should be looking at, especially when the equation is not written in standard form, how do you decide if it's going to be one of these 6? Well, first thing is break it into one of these two categories. Look at how many variables are quadratic, and that can at least help narrow your list down a little bit, especially if one of the variables is linear. Well, now you're down to basically one of two options, right? You're down to the elliptic paraboloid or the hyperbolic paraboloid. If all the variables are squared, well, you still have 4 to pick from. This is where you have to start looking at things like how many negative signs are there in the equation? How many positive signs are there in the equation? Do I have the number 1 on the right-hand side, or do I have the number 0 on the right-hand side? These are all little tricks we talked about last time. So just brief little summaries here for the ellipsoid. All the variables are positive. All the variables are quadratic. That's how you know it's an ellipsoid. The traces in every single plane will be ellipses. In the case where A, B, and C are equal, so if all of those denominators are the same, then you get a sphere, and you actually end up with circular cross sections. The hyperboloid of one sheet, all the variables are squared, and there are 2 positive variables and 1 negative variable. 1 minus sign means 1 sheet. That was the little trick that I told you last time. The variable that's negative is going to be the direction of opening. So if you notice in this case, z is negative, which means that this hyperboloid of one sheet is going to open in the z direction. Traces are ellipses in one direction and hyperbolas in the other 2 directions. And you don't have to memorize all those. You can see that by fixing different values of x, y, and z and having an understanding of your 2-dimensional conics. If you know your conics from pre-calc, you will be just fine determining the traces. Okay, so study up on your conics so that you don't have to memorize the traces in every possible direction. Hyperboloid of 2 sheets looks pretty similar. Remember what we said last time in the last video, 2 minus signs this time. All the variables are still quadratic, but there's 2 minus signs. 2 minus signs, 2 sheets. Okay, and remember there's that gap. There's certain values of z in this case where there's nothing there. Nothing exists between the 2 cups. So it depends on what values of x, y, and z you pick. They will always lie between your intercepts. So once you find these z-intercepts, the surface is only going to exist above that positive z-intercept, and it's only going to exist below that negative z-intercept. It will not exist in between. You will have no surface. Okay? There's your traces, hyperbolas, ellipses. All the variables are quadratic. They call it an elliptic cone. We called it a double-sided cone. Okay. Depends how you write it. There's the case where you could move all the variables to one side, in which case it looks kind of like a hyperboloid of one sheet, except remember here we have equals 0, whereas for the hyperboloid of one sheet, it was equal to 1. So I don't prefer to write it in this form. I prefer to write it in the form where you sum the squares of the two quadratic terms on one side and you isolate the quadratic term on the other side. Just a preference. Either is fine. Depending on which way you look at it, the isolated term is the direction of opening, or if you keep it in the original form, the term that's negative is the direction of opening. Okay. And this is the one case where we actually had these pairs of lines, right? I'm going to outline them in an easier to see color. Here's these pairs of lines that we got that cross through the origin. And so that was actually one of our possibilities for these some of these planes, is we actually ended up getting linear cross sections or linear traces to create the two parts of the cone. Okay, the elliptic paraboloid, now we're down to just two variables that are squared and one linear variable. So the linear variable determines the direction of opening. When you're adding the two quadratic terms, it's an elliptic paraboloid. Look down below. Still, one linear variable determines the direction of opening. However, now we're subtracting the two quadratic terms. In that case, you have a hyperbolic paraboloid. Okay? In the first case, you have an elliptic paraboloid. Would make sense, because when you subtract quadratic terms in 2 dimensions, you get a hyperbola. When you add two quadratic terms in two dimensions, you get an ellipse. So kind of goes with what our intuition would say. The axis of symmetry will always correspond to the linear variable, the one that's not squared. Okay. There's our cross sections we talked about last time. All right, so that chart, especially when you're studying for a quiz or a test, I would definitely use this chart to help you out. Okay. Especially for a lot of that pattern recognition. More reps you can do with this stuff, the better. Okay, so they won't always be in standard form. So that's why it really helps to be able to categorize them into how many variables are squared, because then you go into the problem with a plan. So what we want to do with these is we want to identify and sketch the surface. If it's not in standard form, which none of these are, then we first want to put it in standard form before we graph it. Okay, so first one. I see 4x squared minus y squared plus 2z squared plus 4 equals 0. First thing I notice, all the variables are squared. So if I look back at my list at the top, I can rule out elliptic paraboloid and hyperbolic paraboloid. I know it's going to be either an ellipsoid, a hyperboloid of one sheet, a hyperboloid of two sheets, or a double-sided cone. I do see some negative signs and positive signs. I see mixed terms. So I know that it's not going to be an ellipsoid. So at this point, I'm down to either the cone or one of the hyperboloids. Probably not going to be the cone, because I'm not going to be able to get 0 on one side. This shift by 4 means that I'm probably going to have either a hyperboloid of one sheet or two sheets. So I'm going to start by moving that term over to the other side. Isolate my quadratic terms on one side, put -4 on the other side. Well, if it's a hyperboloid of one sheet or two sheets, I know that I'm going to want to get the number 1 on the right-hand side. So I'm going to divide everything. This entire left-hand side, I'm going to divide by -4, and the right-hand side, I'm going to divide by -4. So I end up with, I'm going to put my positive term first, y squared over 4 minus x squared minus z squared over 2 equals 1. Now it's in standard form. Okay, everything's quadratic. There's 2 minus signs. So this is going to be a hyperboloid of 2 sheets. Remember, 2 minus signs means 2 sheets. Okay. What's the axis? The axis of symmetry is the variable that's positive. In this case, y is positive. So I'm going to say whose axis is the y-axis. Okay, so here's my standard form. Here's my quadric surface. And last but not least, here's my graph. The intercepts, remember, are all for the hyperboloid of two sheets. You're only going to have intercepts along the axis of symmetry. So in this case, I know there's no x and z intercepts. They would be complex numbers. We don't want to do any calculus with complex numbers in this class. If you're interested in that, you can take a whole course in complex variables in college. Very interesting stuff. My intercepts here would be at 0, 2, 0, and 0, negative 2, 0. If I solve y squared over 4 equals 1, there's one of my intercepts at 2. There's another one at negative 2. And we get those two cups of the same size. So there's one cup. And you don't need to be super exact after you. As long as you plot the intercepts correctly and show me the two cups, you're good to go. Okay. Nothing exists between the cups. Okay, those cups are the exact same size. They're just opposing directions. Okay, so that is my hyperboloid of two sheets. Okay, next one. Again, I see three variables all squared. And in this case, it looks like we also have some linear terms. So we're probably going to have to do a little bit of completing the square. We did this with spheres in section 12.1. Now we're going to do it with the rest of our quadric surfaces here. So when I complete the square, I want to get all of my constants on one side. Check. Looks like I already have that done. I'm going to collect all of my x terms together, all of my y terms together, and all of my z terms together. So I got 4x squared plus 4y squared plus 8y plus z squared minus 4z equals negative 4. And I'm going to complete the square on each variable. Looks like x is already good to go. I'm going to factor out a 4 from the y terms. So I get y squared plus 2y. I'm going to leave a space. And we'll complete the square in a minute. Z squared minus 4z, leave a space, equals negative 4. Okay, let's complete the square on y. Cut the coefficient next to the linear term in half. So next to y, I see a 2. 2 divided by 2 is 1. And then I'm going to square the 1. 1 squared would be 1. So I'm going to add 1. Keep in mind, you have to distribute that 4. So you're not really adding 1, you're really adding 4 times 1. So I'm adding 4 to the left. That means I got to add 4 to the right. Let's do this one in blue. Now I'm going to complete the square on z. I look next to the linear term for z. I see negative 4. So I'm going to cut negative 4 in half. I get negative 2. And then I'm going to remember to square that. Negative 2 squared is 4. So I'm going to add 4 to the left side, which means I have to add 4 to the right side. So I get 4x squared plus 4. This now factors into y plus 1 squared, since we completed the square. And this part factors into z minus 2 squared, since we completed the square. On this side, I'm left with 4. Okay. Everything's positive, and everything's quadratic. It's an ellipsoid, which means I need to get 1 on the right-hand side. So I'm just going to finish by dividing out 4 from everything. Divide out 4 here, divide out 4 here, divide out 4 here, and divide out 4 here. So I end up with x squared plus y plus 1 squared plus z minus 2 squared over 4 equals 1. Okay. There's my standard form. This is an ellipsoid. Don't worry, you're going to notice the graph does not intersect where I'm writing. This is an ellipsoid. You don't have to specify the axis for an ellipsoid because it's an enclosed figure. It's not moving in any specific direction. But do specify the center. This is centered at 0, negative 1, 2. Flipping the signs on x, y, and z. Okay, so we also probably want to get the intercepts. So if I get the intercepts, it'll help make the graph. So the x-intercepts are going to be at, let's see, 1, 0, 0, and negative 1, 0, 0. Yeah. So there's my x-intercepts. No, that's wrong. Pause. Where are my x-intercepts going to be in this case? I got to put 0 in. Oh, we're shifted now. Hang on. If I put 0 in for y and z, I'm going to get x-intercepts at, see, x squared plus 1. Oh, they're going to be complex. We're not going to have any x-intercepts. We're going to have x squared equals a negative number. So there are no x-intercepts. Okay, let's do y-intercepts. If I put in 0 for x and z, then I'm going to get y plus 1 squared equals, see, we're going to get 0. Because we're going to end up with a 1 on the left-hand side and a 1 on the right-hand side. So those are going to cancel out. Okay, so I'm going to have an intercept at -1. So at 0, -1, 0, there's going to be one part of my ellipsoid. And then the z-intercepts, let's see, if I put 0 in for z, I'm sorry, if I put 0 in for x and y, I'm going to get z minus 2 squared over 4 plus 1 equals 1. So z minus 2 squared over 4 equals 0. In other words, z minus 2 squared equals 4. If I square root both sides, z minus 2 could equal 2, or z minus 2 could equal -2. So one of my intercepts would be at 4. One of my intercepts would be at 0. No, it wouldn't. Let's see. Z minus 2 squared, put 0 in for x and y. Yeah, there we go. Okay. It's centered at 0, -1, 2. So if we plot that, our center is going to be 0, left 1, up 2. It's going to be in line with this intercept here. Kind of right in line with that. Yeah, and if we graph this, let's kind of just get some intuition for what this should look like. These are a little trickier to graph when they're shifted. We're going to get x squared plus y plus 1 squared plus z minus 2 squared over 4 equals 1. What? Oh, it needs to be an implicit surface. My bad. Let's try that again. X squared plus y plus 1 squared plus z minus 2 squared over 4 equals 1. There it is. Yeah, there we go. Oh, I see my mistake from before. There it is. If we put in 0 for x and y, yeah, this is what I meant to do before. I'm sorry. Oops. The intercepts, you're going to end up with the ones are going to cancel out. You're going to end up with 0 plus 1 plus z minus 2 squared over 4 equals 1. So you're actually just going to end up with z minus 2 squared equals 0. So z would have to be 2. You only get one z intercept. Sorry about that. So there's one of my intercepts at 2. Another one's going to match right about on this side. And then best way to make this picture, let's see. Looks like from the center, it goes down 2 units in the z direction. So it's going to have to go up 2 units in the z direction also. So I'm going to also go up here. Trying to keep that theme of 3 colors going on here. Do the best we can. These are a little trickier. This goes out about 1 unit this way. And so we end up with, yeah, so if we connect our, I'm not going to be as exact as I was with the ones that were centered at the origin. These are a little bit tougher to graph, so I won't be so picky with your graphs for these. But there's the general egg shape. And then, let's see, yeah, we're going to end up with kind of another, we'll get another one connecting. If we do another set of colored dots, generally, there would be my ellipse. Good enough. And that looks pretty similar to, if we look at the graph I made here. Why is this one cut off? Oh, because I restricted the values of the variables. It's not a paraboloid. It's actually an ellipsoid, but it got cut off. So there it is. You can see it's crossing at 0, 0, 2. The other edge of it is crossing at 0, negative 1, 0, just like we had. So there's my ellipsoid. Okay, last one. Notice in this one, I only have 2 variables that are squared. So I am down to either the elliptic paraboloid or the hyperbolic paraboloid based on my chart. We'll have to complete the square before we can decide here. So I'm going to move the 10 over to the right, and I'm going to collect my x's and y's. Let's see. And actually, I'm going to want, since there's a linear variable, in this case, I'm going to want to move that isolated variable over to one side all by itself. So x's I'll still collect. Z's I'll still collect. But I'm going to move the y and the 10 over to the other side. Now I can tell which direction it's going to open. It's going to open in the y direction since that's the linear variable. Completing the square, I would end up with x squared minus 6x. Negative 6 divided by 2 would be negative 3. Negative 3 squared is 9. So I'm going to add 9. And for the other term, what do we got? Plus 2z squared. Nothing to complete there. So I end up with x minus 3 squared plus 2z squared equals y minus 1. You could leave it like that. I'm going to maybe move it over to the left here. This would be perfectly acceptable. I can tell at this point that it's an elliptic paraboloid since the quadratic terms are being added and the one variable, y in this case, is linear. You can choose to leave the 1 on the left or move it back over to the right. I feel like if you move it over to the right, you can actually identify the vertex just a little bit easier. So I think I'm going to do that. This would be my preference. Feel free to leave it in the green part right here if you want. But this would be a elliptic paraboloid. So we can cross off hyperbolic. Paraboloid, there's an O there. With, whoa, pen got funky. With vertex 3, 0, 1. Now, I'm not going to say that the axis of symmetry is the y-axis because it's actually not moving along the y-axis. It got shifted to have a vertex of 3, 0, 1. What I would say in this case is that it's parallel to the y-axis. Whenever there's a shift, you have to be careful about the phrasing. Parallel to the y-axis would be a better phrase. If there was no shift, then I would just say moving along the y-axis. Okay, so it's going to open to the right since it's got positive x and positive z. And it's going to have a vertex at 3 units out on the x. It's not... oh, actually, no, pause. Y in this case is actually 0, my bad. It's going to be 3. Yeah, this is why I kept the y minus 1 over here. My bad. This is going to actually be 3, 1, 0. Because if I look here, x is 3. If I look here, y is 1. Z has no shift. There's no parentheses for z. So it's going to be 3, 1, 0. Apologies for that part. Okay. If you look at it on this side, you can see that if you plug in, yeah, you'd get a 1 there for y. So we're going to get 3. We're going to shift over 1, and it's not moving up in the air at all. So there's my vertex. if I wanted to know where it ends up crossing the y-axis, I'd have to plug in 0 for x and z. So if I do that, I'd get what, 9 plus 1. It wouldn't cross until 10. It would go way out here and eventually cross. So we're going to get a something like that. There's my and this is dipping below the xy plane, just to clarify. So all of this stuff here, maybe I'll outline in green. This is all underneath the xy plane. So that would be my paraboloid. Okay, there's my vertex in green. Yeah, so this one opens to the right since it's positive y. And we have the vertex identified, and we've identified it's parallel to the y-axis. That should do the trick. Yeah, so that's pretty much it. Not a whole lot of new stuff in this video, just a little bit of some algebra tricks with completing the square to identify what quadric surface you're looking at. Again, don't get so caught up if your graph doesn't look perfect. Things you want to have accurate, your intercepts. If there's a vertex involved, you want to have that plotted, and you want to have the direction of opening correct. But if it's not a perfect sketch, it doesn't need to look like CalcPlot 3D. We really just want to get some recognition. Can you identify the quadric surface from the equation? And can you make a basic rough sketch with some of the pieces like the intercepts, the vertex plotted accurately? It'll help a lot when we start doing some calculus with this stuff in the next couple chapters. I will remind you one more time, you don't need to know how to draw a hyperbolic paraboloid by hand. Okay, you should understand the pieces that go into making it in terms of the traces, but you don't need to be able to construct one of these by hand three-dimensionally. I will not make you do that. Okay? If you want to make one and send me a picture, I'll be impressed. Go eat some Pringles when you're studying these. Okay, that should do it for this section. And that wraps up chapter 12. Chapter 13, we'll be getting into space curves and some really cool concepts there. So, all right. Happy mathing.